Hey, my name is Tanmay Shukla. This is Lab 5 Physics 2011 at Georgia Tech. Introduction. The objective of this lab, as determined by me, was to investigate the dynamics of a damped pendulum and to compare its behavior as predicted by a theoretical model with the experimental data obtained in the laboratory. Method. So we used Tracker to extract X and Y position data from video, modified and closed script starter code to simulate the system, and compare observed and predicted motion. Key physics principles. For small oscillations, a simple pendulum behaves like a simple harmonic oscillator. Its horizontal displacement can be modeled using the SHM equation, which is x equals the displacement along the x-axis equals a cos omega t plus phi. Similarly, displacement on the y-axis would just be a cos omega t plus phi. Same thing. So here a is the amplitude, omega is the angular speed, which is just root g over L in the case of the pendulum we're studying, and the phi is a phase constant. In this case, we're assuming the phase constant to be 0. Position of the pendulum of the bob can be expressed in Cartesian coordinates relating the angle theta to the bob's displacement. So x is equals to L sine theta and y is equals to negative L cos theta. Experimental setup and initial data. Experimental setup. So a pendulum is constructed by suspending a bob from a fixed pivot. The pivot point is precisely located at 0.24, 0.07. Measurement and data collection. The motion of the pendulum bob is recorded using a video tracking software. Initial position and length measurement. The initial position is taken from the first set of data points. The distance between the pivot and the initial bob position yields the length L of the pendulum. Initial data. Initial position. The initial position of the pendulum is 0.071895, 0.142121, 0, and the initial velocity is as seen, and the pivot position is also as seen. And the effective pendulum length L can actually be calculated just by using the distance formula, since we know the pivot position and the initial position of the bob. So we just use distance formula, subtract the 2 points, square them, and do the sum, and we get 0.583. This is the tracker video. So this is the bob swinging along. We auto tracked it and then graphed the curves that you will see in the next slide. So here, this is the curves we got when we actually graphed and auto tracked. Sorry, when we auto tracked the bob oscillating. This is the X, and this is the Y. There are slight variations in the Y, and that's just because of resistance and air resistance, drag. There's also could be loss due to actually friction in the pivot. So yeah, that's why it varies there. It could also be a little bit of experimental error as well. So gross slip initial condition, G is 9.8. We define L as I described previously. Theta is the angle from the vertical, and that's just the x. The tan inverse using trigonometry can just be tan inverse of the x over y. Then we have the initial velocity, which is as defined. Then theta dot, which is the initial theta at any point, while position, and the rod axis, which is the axis of the actual strength. dt is our time step, which is 1 over 210, which is an integral multiple of 1 over 30. Our total is t total, like how long a simulation time we're actually looking at, is 5. And yeah, and this is the calculation loop. So we loop over and we get x and y as described as L sine theta and L cos theta, and then we actually graph it and we update a position based on the position update formula and the velocities per the velocity update formula. And when we actually run it, this is how the graph of x position with time for experiment versus model looks. So you can see pretty close, and the red graph is slightly grainy, and this is because of there's time steps between each point we actually graph the x coordinates. So yeah, and yeah, it's actually below the model just because of damping. So essentially, each time it oscillates, it loses energy just because of interaction with air particles. So yeah, that's all it's saying. Similarly with y, again here it looks pretty sporadic and erratic, and that's again just because of yeah, interactions with the air, damping, oscillation, friction, and also I think there's a bit of experimental error here as well. Maybe we didn't define the tracker initially correct, or something messed up the y values, but yeah. Sources of error. So the measurement of pendulum length, uncertainty in actually measuring distance from the pivot to the bob center of mass can lead to an incorrect value for L. There's pivot friction air resistance as discussed previously. The real life damping may be higher or lower than predicted. Then there's small angle approximation limitations because we assume theta to be sine theta for small angles. This could be not true if the if the displacement wave was led at was actually not a very small angle. Timing and sampling rate, so inaccurate and inconsistent time measurements. Discussion questions. First question is, what would happen to the experimental data if the air was thicker or if the pivot experienced more friction at the point of contact? So as discussed previously, if the air was actually thicker, it experienced more friction. There'd actually be greater loss in energy over time just because of interactions with the air or interaction with friction, which result in a faster amplitude decay and a lower time period. And if the pendulum's initial displacement was increased beyond the small angle approximation, so one of the assumptions we actually made was that for small angle sine theta equals to theta. So if that assumption doesn't hold, then we wouldn't be able to actually approximate theta as sine theta in the time period equation. So that's it. Thank you. I'm Tamesh Shukla signing off for Lab 5 Physics 2211.